All right, it's the top of the hour. Let's go ahead and get started, and if anyone else joins, they can catch up. This particular presentation tends to be somewhat fast-paced. We are going to show some code examples, some SQL and Postgres examples, but the bulk of it is really around the slides and the process of what do you do to create a database design? What's the process and what are the steps? So let's just dive in. At any point, if you have questions or concerns, if I've said something that's confusing or you want to dive deeper into something, please either speak up in the voice channel or you can post your comments in the Google Meet chat. Either way works. So uh, this particular roundtable again is going to present a basic design workflow. So you will see as I go through this, I want to point out errors that I made in the design as I was doing this, and also I'll point out some areas where I could have done better. So this is a very basic design flow. Um, It focuses on SQL or SQL. SQL stands for Structured Query Language, like Postgres or MySQL or Oracle. Those are all based on SQL. But the concepts we're going over also apply to NoSQL databases like MongoDB to a certain extent. Um, One of the things we're going to really stress is, how do you identify and implement relationships? Not just the data entities and the attributes on those entities, but how are the tables and the data related to one another? Now, we're going to follow this up next Wednesday. That's the 30th of July. Andres is going to be diving even deeper. We are going to cover normal forms today, the first three, but he's going to dive into the remaining normal forms. There's actually, I think there are 6 or 7 normal forms, but there's another 2 or 3 kind of add-ons, if you will, principles that complement normal forms. So there's actually a total, if you will, of 9 normal forms. Um, Again, the first 3 are the ones that are really the most important, and those are the ones we're going to go over today. So yeah, Andres is posted some clarifications in the chat. So thank you for that. Um, And with that, let's move on. Now, one of the things to keep in mind is a 1 hour session like this isn't going to make you an expert. And that's not our goal today. But our goal is to provide you with the information and the terminology and a process that you can follow to practice building data, designing databases and building them so that you can build up that expertise so that in a month or 2 months or 3 months, you can become an expert. Again, at any point, if you have questions, please post them in the Google Meet chat or speak up in the voice channel. Either way is fine. All right, so let's go through the design workflow. What are the major steps we're going to follow today? Well, first of all, just like anything else in application development, to design a database means that you need to understand the application requirements. So we're going to be looking at the product backlog as the source for what our requirements are. And before we even start designing tables or deciding what columns go in a table, we're going to have to understand these application requirements. Because ultimately, just like your application, the database has to design and has to meet the requirements that the users impose, not the requirements that developers need. So again, we're not designing something for us. We're designing for a particular group of end users. Now, once we've understood the application requirements, then we're going to create an initial diagram. This is called an entity relationship diagram. And we're going to go through it in multiple iterations. We're going to look at those application requirements and match them to our database concepts to basically build up in a top-down approach our entity relationship diagram. Now, once we've done that, once we understand what is the data that we're going to manage and what are the relationships, then we're going to normalize the schema. And again, this refers to applying the first three normal forms to the data. And don't worry about normal forms. It's something that many developers and even many database administrators find a little bit daunting. But it's after you understand the concepts, it's really fairly straightforward. So once we've normalized the schema, then we're going to implement the tables. And following that, we'll implement the relationships as well. And then once we've done that, once we've, number 4 and 5 really refer to defining the structure of the database in a particular database management system, like a Postgres. Once we've done that, we'll need to load some test data, and we need to make sure our test data, matches our requirements, or at least reflects what's needed in our requirements. And then we'll create some queries to run to basically identify, does our database actually meet the requirements? So some terminology right off the top of the session here. Entities at this point are very generic. They refer to the set of data that we need to manage. The relationships support how those entities are used. So an example is that I may be an end user. I may have a user record in an application, and I may have chosen a particular OAuth authentication scheme when I registered my account. So I could have chosen maybe Google or GitHub, for example, or maybe just a simple user ID and password scheme. Well, that relationship between the user and the OAuth scheme that user wants to use, that's a relationship. It's two separate sets of data that are related to one another in some way. And in fact, I'm sure you've all heard the term relational database management system. Relational refers to the relationships that exist between the physical data elements or data entities. So anyone have any questions or comments or concerns? Those are always valid too. Okay, we'll move on then. All right, so our first step, we need to understand our application requirements. And the reason for this is that the database has to support the application. Has to support the developer's application code that they create. And specifically, developers are going to write code that will navigate through the database. At different points, they may be wanting to get an account table, a row for a particular user, or they may need to get a customer row. It's basically that navigation is what the database needs to support. And so to do this, we need to identify what are the major entities, the groupings of data, and then what are the attributes or the columns in each of those tables or entities. And again, that's all going to come from the requirements. And then the third thing we're looking for is we need to understand how's the data going to be used. What are the queries and the reports and whatnot that the developers need to create? Once we understand that, well, that'll also give us a better insight into what navigation capabilities and relationships we need to build into the database. And then finally, we mentioned this before, but product backlog items, your product backlog is going to be the guide to what's required on the part of the database. So we're going to use it as essentially our set of data or specifications that we need to design to. So let's take a quick look at what are some application requirements. So in this particular application, it's a very simple one. It's basically an application that lets users maintain a record of books they've read. They can categorize their books in any way they want, but as long as it's using a predefined set of categories. So again, I could have read Mark Twain, Huckleberry Finn by Mark Twain, and Lisa could have read that same book. While I might have classified it as fiction, she might have classified it as a category of humor. Okay, so we can both categorize a book in different ways, but we share that predefined list of categories. And then the last thing we need to be able to do is we need to share comments about a book. So, for example, for Huckleberry Finn, I may have comments I want to share with other users. Lisa may post comments about that book that she wants to share as well. Now, this particular application, I've intentionally kept it really, really simple. It's basically, it's oversimplified because I don't want the application requirements to be so complex that it makes it difficult to go or to understand how to design the database. So as you're going through this, I'm sure you will think of features that you would like to see in this application. The reason we've omitted them is again, we don't want to draw a curtain over, we don't want to make it harder to understand the process of database design. So any questions so far about the application requirements? Okay, don't hesitate to ask questions. I guarantee that if you have a question, someone else has the same question and are just too shy to ask it. One of the things that we value at Chingu is the power of questions, but also the power of having different opinions. That's how we learn, is through this give and take of different opinions and by asking questions. So you will never be yelled at or picked on because of a question you ask at Chingu. That's something that's at our core set of principles and beliefs. All right, let's move on. So from that set of requirements, we can identify some entities and some attributes. So the four entities are fairly obvious. There's books, categories, comments, but then there's also a reader. In order for me to share my comments about a book, or for me to share or keep a record of what books have I read, there needs to be an entity that defines, Jim as a reader or Andres as a reader. So the attributes of each of these entities, you could think attributes will turn into columns. But for books, we need to know what's the title of the book, the author, the publisher, and the date published. Categories are really simple. We just need to know what's the category name and its description. For comments, we need to understand when was the comment posted, and obviously what is the comment that someone posted. And then finally, for a reader, we need to know that individual's name, their country, and the date that they joined this particular application, the date that they registered. And we're going to keep it this simple. We're going to add a few more attributes in a moment and a couple new entities as well. But again, our goal is to keep this as simple as possible. I want to make sure I didn't miss anyone's comments. Okay, cool. All right, so how is this data going to be used? I've always found it useful that before I really start defining a detailed entity relationship diagram, I
Jim,
like, yes, go ahead.
sorry, ATK has raised a hand. Maybe he has a question.
Oh, I'm sorry. Thank you. Yeah, go ahead,
Hello.
AJ.
Please, I wanted to ask if the database structure is it a SQL database or a
Oh,
document-driven
I'm
database?
sorry. You're coming through. You're really muffled. I'm unable to understand what you're saying.
I wanted to know if we are dealing with a structured database or an unstructured database.
Yeah, I apologize. The sound is
Yeah,
really not coming
I
through
could hear
well.
him. I could hear him. He said he's asking if we are using a SQL or no SQL.
If I'm using what? Oh, SQL or no SQL? In this
Yes.
presentation, we're going to use SQL, but a lot of the concepts up to a certain point will be very similar. Uh, because whether you're using SQL or NoSQL, you're identifying entities and attributes. And even in NoSQL, you're identifying and managing relationships as well. But all of our code examples will all be in SQL. Thank you for that,
Okay.
Bobo. I appreciate it. All right, so before I start to define an entity relationship diagram, I like to just sketch out what are the kind of the facts that I know. What are the high level entities I've identified? So in this case, I know that there's a reader, and it's going to be created when someone registers, and then it'll be referenced when they log on to the application. There'll be comments, books, and categories, and those will be maintained through your traditional CRUD type of operations. CRUD is CRUD. That stands for create, retrieve, update, and delete. And then the group of users is fairly simple. In a more complicated application, you would have users that have different roles. You may have a user that's a manager, a user that's a clerk, a user that's a casual end user or a guest. In this case, we just have one category or one role, which is user. So relationships will come in just a moment because they're obviously fairly important as well. So now that we've identified what are the major entities and what are the points where they're used, now we want to create our initial entity relationship diagram. This is going to be a very top-down approach. You'll see, in fact, if you've got the slide deck that I posted in the town hall chat channel, you can see that there's many iterations of this ERD. Basically, what an ERD does is it allows you to visually represent the entities, attributes, and relationships between them. So it's a way of basically drawing a picture of what the database looks like. And the purpose of this, a picture is always easier to understand than words. So this is going to help you understand what's the structure of your data, but also what's the flow, what's the navigation between the entities. And there's an old saying, I'm sure you're probably familiar with it, a picture is worth 1,000 words. That's the purpose behind an entity relationship diagram. So the first iteration of this, I've mapped out 4 entities, and in each entity, there are a set of attributes. So we've got reader, book, category, comment, and then you can see under reader, we've got the 3 attributes that we identified earlier, but I also have an array of books that contains, what books has this particular individual read. Now, one big controversy in database design, it's split by about half and half if you talk to any developer or database administrator. Some people prefer to call their entities using plural names. Pardon me. So they would have named this readers, books, categories, and comments. I prefer, and there's no clear majority. It's about a 50-50 split. I prefer the singular. So I prefer to refer to these as reader, book, category, and comment. Again, there's no right or wrong. As you work through this and as you practice, you'll hit upon a style that makes sense for you. So this is our first mapping of entities that will become tables in our database. So the next thing we want to do is we want to add relationships to this. So rather than giving this a complicated name or a long description, this is just my preference. I like to just map it to a particular PBI, product backlog item. So in the case of reader, remember that our first requirement was that readers need to be able to maintain a list of the books they had read. So there is a relationship between reader and book. And then likewise, between book and category, we said that a particular user should have the ability to map a book that they've read to a particular category. And so that's that application requirement number 2. And so on. So any questions? Can anybody spot the flaw or one flaw in this particular diagram at this point in time? There is a big one, actually. No takers. Okay. Well, I'll tell you what it is. The flaw is that we said that users should be able to categorize a book individually. So again, that example I gave earlier, Lisa could categorize a book as humor, while I could categorize the same book as fiction. Well, this database design doesn't support that. This relationship between category and book only supports a predefined association of a category to a book. So that's something that I'm pointing out, because as you go through that process of database design, you'll find errors in each of these iterations, which is the reason why you iterate, because you find errors and you fix them. So now that we've got an ERD, let's normalize the schema. So what the schema is, a schema is a way to organize tables and relationships. Really, you're working towards we're going to update the diagram, but we're normalizing it so that data can be easily maintained and it's a little easier to read. Again, as I said earlier, there are multiple what are called normal forms, which is a relational calculus, an attribute of relational calculus. The first 3 normal forms are the ones that get you the most benefit for the amount of effort you put into using them. Also, I don't want to scare anyone. I said relational calculus. We're not going to go over calculus or formulas in this. These normal forms, there's some very practical rules you can follow so that you don't have to memorize formulas. And again, Andres is going to cover normalization in part 2 in quite a bit more depth. Like I said earlier, really the goal of normal forms, it's to eliminate data redundancy and improve the integrity of the data. And what this does, the practical advantage is it makes your database less brittle. If something is brittle, any amount of tension tends to break it. Like if you have a board or a ruler and you put a little tension on it, it's going to snap because if it's made out of wood, because that's a brittle material. Well, what normal forms do is that they make your database design easier to modify, easier to maintain, because we know that changes are going to occur over time. It's a fact of life. So let's look at what are the most common normal forms. So first normal form, what it really says is each column has to contain a single value. It can't contain embedded arrays. Uh, and so if we go back to that ERD, remember I had this books array? This is going to be removed, and we're going to implement this as a relationship between rows in the reader table and specific rows in the book table. And the reason for this is that, just think, if you embedded an array in a table, what's the maximum size of that array? I can tell you it probably doesn't matter what the maximum size is because sooner or later you're going to hit it. Some user is going to want to log the fact that they've read 10,000 books, and your array may only be set up to support 1,000 books. Well, by implementing the relationship or this record of which reader has read what books as a relationship, it means that there's no practical limit because there is no array. So the second normal form says that all of the columns in the table have to be solely dependent upon the primary key. So in each table in SQL, each table has a primary key that's unique. So if you find that a column isn't dependent upon the primary key of the table, that says that column should probably be a member or an attribute of a new table. So let's take a case in point. Let's say that, well, let's use a Chingu example. Let's say that you have a voyage. You're signed up for a voyage, and as part of that sign up, we ask for your time zone. But time zone isn't really dependent upon the voyage sign up. It's really an attribute that's dependent on you and as an individual. So that time zone should be an attribute in a different table, like the record of you as a Chingu member, as opposed to a voyage sign up. That's an example of a column that's not dependent upon its key. Whereas in a voyage, the tier that you signed up in, that is dependent on the voyage sign up because it could be unique to each voyage. You might have one voyage where you're a tier 1 and a different voyage where you're a tier 3. And then the third normal form is a case of transitive dependencies. So let's say that you've signed up for a voyage and we've asked you for your nationality. That nationality isn't dependent on the voyage sign up record. It's dependent upon your user record. It's an attribute of you as a particular user. So that's what we call a transitive dependency. And as you can kind of imagine when you look at these, first normal form is very practical. Second normal form is practical as well. Third normal form gets a little bit more esoteric. And as you go into the more advanced normal forms, they also become a little more esoteric. They become a little harder to understand and a little more difficult to implement. Yeah, you're absolutely right, ATK. Voice cod normal form is used in the industry a lot. Um, just to take a pause, SQL, basically relational calculus and relational databases were invented by, let's see, what was his name? CJ, EF Codd and CJ Date, actually, were the two researchers' names. They were both working at IBM in the late 60s and early 70s when they came up with SQL. And SQL is based on this relational calculus and relational concepts. And I don't remember about Boyce. I don't remember his history, to tell you the truth. Um, so, any questions? All right, let's take another look at this. So in Reader, remember we had that books array? Well, we've removed it, and in its place, we've created a Reader Books entity that contains two columns. It contains the unique identifier of the person who has read the book, and then the ISBN, which is an international numbering scheme for books. It contains the ISBN that uniquely identifies a particular book that they've read. Now, the other thing we've done at this point, this really is kind of a starting point to normalization. We identified what were the primary keys in each of these entities, and we assigned them. So we've arbitrarily assigned a unique ID number that's a primary key. That's what the PK stands for reader. And then the same is true for comment and category book and book. Now in reader books and reader comments, the primary key of each row of reader books is the combination of the reader ID and this ISBN number. And similarly, reader comments, the unique primary key is the comment ID and the ISBN together. So the way this works is, let's say again that I've read Huckleberry Finn. So if my reader ID is 001, we would have a row in reader books where the reader ID is 001. And then the ISBN number is the unique identifier of the book Huckleberry Finn. And then we would have a book that for Huckleberry Finn that has its unique ISBN number, and then the title and the author and whatnot. So when we want to see all of the books that Jim has read, we would start at reader. We would retrieve all rows in reader books where the reader ID is 001. And then we'd navigate to each of those rows to access the book to produce a list of, oh, well, here's the list of books that Jim has read. Here's all the titles. So you can see there's a many-to-many relationship between reader and reader books. And there's really this is really a one-to-one this is a one-to-many relationship between reader books and book. So any questions? I say that the many of this, actually this is not, this is a one-to-one relationship. Because for this row, for a row in reader book, there's only one book that it can be joined to. Okay, any questions? How's this level of detail? Is this too slow or too fast, or is this information actually useful? Okay, I'm just going to go on. Again, feel free to ask questions or to disagree. So now we're down to the point we've got our ERD defined, we've got that relationship defined. Let's implement the tables now. So this is going to be very specific to your database management system. So a DBMS is a generic term for a very specific implementation of a database. So Postgres is a particular DBMS. MySQL is a particular DBMS. MongoDB, even though it's NoSQL, it's still a particular implementation of a database management system. So the first thing we want to do is define our entities. And we're going to use that diagram as a guide to creating the syntax. And again, our tables are going to represent, we're going to create a table for each entity. And for each column in that table, we're going to use the list of attributes in the ERD to define those. And something else that's important is we need to choose the correct data types. We need to be sure that we're consistent in our use of data types. And I'll go over that in more detail in a second. So, for example, here we've actually lowercased the names of the entities. These are now table names. When I was talking about making sure you use consistent data types, we'll see in a minute that ID I defined as a numeric, as an integer. So I need to make sure that ID, if it's defined as an integer in the reader table, it's also defined as an integer in the reader books table. And likewise in the comment table as well. So I need to be consistent with that. Oh, cool. I'm glad to see that, ATK. I'm glad this is helpful. And then the same is true for like categories in books and reader comments in books. You need to make sure your data types match. So now that we've got that, we have our names have been listed in the ERD using the syntactical conventions of our DBMS. We're going to do the same for relationships. Again, we're going to map out our relationships between the tables. We're going to make sure that tables have the correct primary and foreign keys. Again, primary keys uniquely identify rows within a table, while foreign keys are attributes that link a row in one table to a row in a different table. And that creates that relationship. And then one of the things we can also do is we'll take a look at our database and we'll see, could we optimize by adding additional indexes on particular attributes of a table to make access very fast? And this is an oversimplification, but if you're not familiar with indexes, you can think of them as basically they implement a type of binary tree search on values in a particular column or set of columns in a table. So it makes it very quick to find particular rows in a table based upon some column value. Now, there are different types of relationships. There are one-to-one relationships. So, these are peer-to-peer. For a single peer on one side, there's a single row on the other side with the same value. So, an example of that would be, let's go back to our user and authentication type. If we have a table called user, and we have a table called authentication type in our application. And if the business rule says that a user can only have one current authentication type, then we would have one user row would be joined to a particular authentication type for that particular user. And presumably it would have some other column values that are unique to that user as well. That the combination of that user and that authentication type. Now, one that occurs, I think, more often than not is a one-to-many relationship. You can think of this as a parent-child type of relationship. So let's say that we have a salesperson that's a parent. So we have a table called salesperson, and then we have a customers table. Well, that salesperson has a fixed set of customers. So in each of the rows in the salesperson table, we would have a foreign key that's the unique ID of that one salesperson, the one individual that sells to them. So that would let us navigate to the salesperson table and then join it to all of the customer tables based on the salesperson ID to get a list of who are all the customers that this salesperson is sold to. And again, there are lots of business rules here. In that particular example, the business rule says that salespersons are owners of customers. That if there's 10 salespeople in the company, they all have a unique set of customers that they service, and that they can't sell to a different salesperson's customer. Now, the other thing, other example, which we saw, or I should say relationship type, which we saw earlier, is a many-to-many. So this is that case of a reader on one side and book on another. The reader, Jim, could have read, 10 different books. The reader, Lisa, could have read 15 different books, 5 of which are the same as the one Jim read. So it's really a many to many. You could go from the parent side, you could retrieve the user or the reader, Lisa, and get a list through the junction table of all the books that she's read. Or you could access from the books table, joining on the junction table, to see who are all of the readers that have read Mark Twain. So it works in the opposite direction. Any questions? All right. So in this case, what we've done, we've just updated our ERD diagram with, again, some relationship names. These are names that we will use in our actual SQL definition in Postgres. And we've mapped what type of relationship is this. And again, in this case, this is an error that I made. The ISBN in reader books is related to a book. It's a one-to-one relationship because we're joining on ISBN number. And the same is true for reader comments. So any questions? Let's take a quick look at syntax, because now that we've got it, we've taken our ERD diagram and we've turned it into what's called a schema diagram. This is basically a diagram of the database that's specific to a particular database management system or DBMS implementation. So let's go over to Visual Studio Code real quick, and I'll show you what this looks like. So this particular schema, you can see I've got a reader table. It has these columns, and each has its own data type. And we've defined the primary key as being the ID column. Now, I didn't have to define an index on ID because Postgres assumes that every primary ID will be created with an index. It will do that for us. And then on comment, again, it has its own unique ID, but it also has the ID of the reader that created that comment. Something that's a little more interesting is down in reader books and reader comments. We can see that they have a primary key that's the combination of reader ID and ISBN. Now, what we might also do here is we might have defined an index on ISBN to make it fast to retrieve, given an ISBN number, who are all the readers that have read that. That would allow us to read all or retrieve all rows in reader books with the same ISBN number. And then we could use the reader ID in those rows to retrieve the reader table. Now, one other note here, and this is where those application requirements come into play again. This is why they're so important. ISBN is a varchar of 17 with a max length of 17. That's because if we looked up the definition of the ISBN number, it's essentially an international standard that publishers follow. It has a max length of 17 and it has a particular format. If we want to get complicated, it has two formats. It has a 13-character format and a 17-character format, but we're not going to worry about that at this point. So this is our set of tables, and then we've defined relationships. On the comment table, we have a foreign key defined on the reader column that references the reader table based on a common ID. And I think this will become a little more apparent. I've created some test data and loaded it, but let's actually run this. And we'll look at some of the output. So let's go down to list all books for each reader. Yeah, so this is the output from this select. So in this case, what we've done is we're selecting rows from the reader table and rows from reader books where they have the same reader ID. And then we're retrieving books where the books have the same ISBN number as the row in the reader table. And so what that gives us is this list of, I want to make sure I've got the right one. Yeah, that gives us this list of readers and all the books they've read. Any questions at all? So let's go back. Oh, go ahead. Let's see, to design and normalize a database, I like to work with sample data. That way I can visually see what data redundancy may appear. Yeah, that's a good point. The other advantage of that is this is the file where I created my test data. It's really overly simplified. But the other advantage of doing it that way is when you define your data, if there's some flaw in the database, let's say, for example, there's a flaw that doesn't allow a comment to be joined to a reader row based upon a relationship, this insert would have failed right then and there. So that gives you a way to as you're creating your test data and actually running it, once you've defined your database, it's another check and balance. It's another way to validate that the database design is correct. But as Andre says, that starts with having a good set of test data. The other thing which is true of test data here, as well as the tests you create for applications, you want to try to break this. While these are all inserts that work, it wouldn't be a bad idea to try to create inserts that are incorrect, or a set of test data that's incorrect, to make sure that they get rejected rather than accepted. Now, one thing, this is another kind of caution or just observation. watch what happens here when I put a comma. I have this repo hooked up to Copilot, so it will create test data for me. One caution here is I'm doing this because I'm pretty familiar with database design, pardon me, and specifically SQL. I would say that if you're just learning SQL, don't use AI to create your test data. Create your test data on your own, and think about again these mappings. Uh, as Andres had pointed out in the chat, you want to be very careful about your test data you create. And what I do is even if even if I let AI create it, I still check my test data. I don't just blindly accept what AI has created. I'm just adding a few more rows in each one, and we'll run this and we'll see if how it works or if it works. So bear with me here while I type while you watch. All right. So I preceded this test data with these delete commands. These are SQL commands that are actually fairly dangerous. These will delete all the rows in each of these tables. But that's okay because this is the way I'm doing this allows me to recreate my test data. So let's go run this and we'll see if it works or not. And it says it worked. So let's go to list the test data and let's run this. Oh, I have to connect. And it appears to work. Now, again, I'm not going to go through this, in this presentation, but what I would do in real life, I would go through each of these very carefully. Uh, and I would examine the database to make sure this all is correct. And I would match it up again against the application requirements to make sure there's something I haven't missed. So any questions or?
Yeah, Jim, I have a question.
Certainly, go
So,
right ahead.
yeah, so just a use case, a scenario. If, for instance, you're building an authentication system, and of course, you will need to have a users table, right? So basically, the question is, I'd like to know, would you prefer to separate a user and his profile, or would you put that in one table? So what's like the trick I should use for normalization in such cases?
That depends. What I would lean to is starting out with just a user profile, and then I would see though from the requirements, is there any reason to create another table? Um, if the profile contains everything that I needed, then I would just go with the user profile table. Um, where I might have a separate table, and this is stretching it a little bit. If there was some data that was very, very sensitive, I might have a separate table so that I would be sure that that's maintained separately. But I think that's really stretching the example. I think that to determine if you
Yeah,
need a user
particularly
profile.
the reason I'm asking is for instance, the login data for like the passwords, the emails, and all of that. those are things you'd like to keep secret, right? Because
Yeah.
it's kind of the identity for the user or the user. So what's the advice? Should I keep that separate for security reasons, or can I just merge the user and his profile? And
Yeah.
I'd like to know if there are any like pitfalls with doing that.
I tell you, the main pitfall, I think, I'm going to back away from what I said. I think in this case, there'd be no need for two separate tables. What you might want to do is encrypt the database, though. And the pitfall in that is you have to be very careful about maintaining your keys. And you also have to be careful that you only access that database from a back-end application server, because there's no way to secure a front-end application. In other words, let's say you had a front-end application in React and you were directly accessing the database from it, a hacker could get into your PC, your session, your front-end session, and they would be able to access your database. So the answer to that is, for that really sensitive information, I think you'd want to encrypt the database. And you'd also want to make sure that your application architecture accesses it through an API from the front end to the back end.
Okay, I think I get it. So it's actually okay to leave them on one table, but then I'll have to take some other measures for security.
Yeah, that's exactly right. And what many companies do is that someone or a team will design a database, but before they're allowed to go further, especially in a large company, someone from an information security department will review their design to help identify things like, well, is it really secure, or what are the weak points in it, and what are the suggestions for correcting those? But yeah, in this case, I think you're better off having one table. Again, as long as you handle the security aspects. That's a really good question too. That's a difficult question to answer because so much of it depends on the requirements as well. You'll find in IT that the most common answer is it depends. Pardon me.
It really depends.
It really does. Yeah. Yeah. So let's talk real quickly about testing and refining. We've really already covered this when we were going through the examples. But again, after you've defined the database, you want to create a set of sample test data, and you want to make sure that it represents the requirements of the application. And I say test data, you'll also want to create some sample queries for each of the requirements. You want to run that, and if you find issues, you need to obviously fix the database design and rerun the sample data. Now, something else to think about is that you don't want to ignore performance either. If your application, if there's some objective that says we want user response time to be no more than 3 seconds, well, when you run these test queries, if you have a test query that takes 4 seconds, anything greater than 3, well, that's an indicator that you need to refine and do some performance tuning on the database. So it's always better to think about performance and security at the time you're doing design and implementation rather than leaving it till later. Oops. And again, what you'll also find is that while you're extracting the requirements from the product backlog, you'll also find it works the other way, that as you're doing the design, you may find weaknesses in the product backlog. It could be something that's not quite correct, or it could be something that's incomplete or missing. So you'll work with your product owner and your scrum master and the rest of the team to make sure that the product backlog and the database design are in sync together. Yeah, what Andre said, we mentioned earlier, but it's true. When you're coming up with test data and coming up with queries as well, try to think of some examples, some things that should fail, and test them to make sure that they do fail. So any questions or? This is actually, we're at the end. Is there anything else anyone wanted to discuss about this or any other questions about Chingu at all?
Can we go back to the relationship, the ELD,
Certainly.
particularly the reader books table? So you mentioned it's supposed to be a one-to-one relationship. Can you clarify that to me?
Yeah. Oh, actually, sorry. Yeah. So in reader books, we've got it's basically the relationship between the ISBN column in a particular reader book row and a row in the book table. This is not a many to many because one ISBN maps to one ISBN in book.
Jim,
Yeah,
it's correct it being one many to one because one book can be read by many readers and one reader can read many books. So for each ISBN you can have many readers, and for one reader you can have many ISBN. So
Yeah, that's exactly
yeah,
what I was
you're right.
thinking. I
You're correct.
I feel it's a many-to-many relationship.
Yeah, you're correct. You know what my error was here? And this is an easy error to make. I was looking at this from the perspective of a single column, but the primary key in reader books is the combination of these two columns. So you're absolutely right.
and that's why I I start my design on a spreadsheet. I don't start my design on an entity relationship tools, because that way I can see the data and see if, okay, yes, this is a one to many, this is one to
Sure.
one. It's easier for me to go from the data rather than from a first level of abstraction.
Yeah, that's a good point. And another technique that you might use, especially if you're doing a modification or an enhancement to an existing application, you have the opportunity to basically create that spreadsheet from data that already exists. So it helps you in mapping new tables and new attributes or new columns, I should say. Now, if you're designing from a brand new database, then absolutely you've got to create that manually. But yeah, I stand corrected on this. You're right. So, what other questions, comments, anything? I really appreciate your interaction as well. That makes these types of presentations far more valuable. Uh, and believe it or not, I do make an error from time to time.
From
I
time to
guess we
time,
all do.
Every now and then.
just from time to time.
Yeah, yeah. I think my biggest, yeah, never mind. I have to remember we're recording this. So, what other questions, comments, anything at all? I will say too, one of the things that comes up that I hear a lot is I hear people making value judgments about libraries and frameworks and databases. So, for example, databases, I hear people say Mongo is better than Postgres, or Postgres is better than Mongo. And that's really be careful about falling into that trap. There are Uh, there are databases that are better than others for particular use cases, but in general, there's no such thing as a database that's just totally bad and another database that's totally good. And I'll give you a practical example of that. I worked at a company, it's been too long, it's been 7 years ago now. I worked at a company where in our information security department, we had lots of security equipment and software running. And each one of those pieces of equipment generated a lot of log entries. So we had equipment that monitored traffic coming in from the outside, coming from the internet, trying to access our private network. And we had software security systems that monitored the behavior of application software even, and they generated log entries. Well, we quite literally, we had, conservatively, we had hundreds of thousands, if not millions of rows of log data every day. Well, we needed to keep that log data for analysis, but we couldn't record that using something like a Postgres because Postgres IO is a little bit slower than Mongo. It's mainly because of all of these relationships. So what that company chose to do is that they recorded all of that log data at the time it was generated in a NoSQL database. It was basically a big blob of data. And then in the overnight hours on third shift, they had applications that read those blobs of log data and structured them and added them to a SQL database. So in that case, the use case that said, I need to record this data as quickly as possible, well, the best database for that was a NoSQL database. But the requirement that said, I need some structure to these log entries so that I can analyze them to find, security breaches and security weaknesses, that needed to be done in something like SQL. That was the best solution. So that's just a practical example of be careful of applying a label of good or bad to anything that we do. I hope that makes sense. So anything else? We are we're an hour, a little over an hour into this. Do you have questions about anything else? Not just this, but Chingu or voyages or anything at all? Okay, we're going to close this one out. I think my most important slide is at the end, where next week, next Wednesday, Andres is going to talk about normalization and give us more insights into that. And you'll also see his design strategy. He does design a little bit different than I do. So I think it's good that you see his way and my way as well. Also, just a note, there's no roundtable tomorrow, and there will be no roundtable on Saturday. I apologize for that. I've got a scheduling issue. So next Wednesday, the 30th, will be our next roundtable. So with that, last call for questions. Otherwise, we'll close out this session. Okay. Everyone have a great rest of your day or your evening, and we'll talk to you all later. Thanks. Bye-bye.
Thanks. Bye, everybody.